So now we're going to start talking about the math portion of this chapter. So we're first going to start talking about units. So units are standard quantities that we use to describe certain properties. So for example, length, mass, time, temp, and amount. Those are the, what is that, 5 that we are going to be dealing with in this class. Electric current and luminous intensity, that's more physics. We don't really mess with that in this class, luckily, but the rest of them we do. Knowing the units for each of these properties is very important, and specifically there is a system that scientists use to as our base of all of our units, and this is called the International System of Units. It comes from a French, the French name for it, System International, but all you have to know is that they're SI units. And we often call this the metric system as well because it uses nothing but metric measurements. So for length, it's the meter, mass, kilogram, time, second, temp, Kelvin, and amount, mole. So mole and Kelvin are probably the ones you maybe haven't heard of. The rest of them you probably heard of. So we're going to be talking about those. Now, this is a very important part to measurements and converting between measurements. This is called prefix multipliers. You most likely have heard of some of these, centi, milli. When we say a millimeter, when we say a centimeter, you guys have probably heard of these. Now, all of these prefixes, we can put them in front of any measurement. Each of these prefixes means something different, and they all have to do with a base of 10. So they all have to do with a you will also hear the word magnitude of 10. Now it's either that they multiply the unit. So let's say we're looking at, let me get my laser pointer. Let's say we're looking at meter, right? If you have pico in front of that meter, pico means that this is a very small number. So 10 to the negative 12 is tiny. Look at how many, it's 0.00000, however many, in front of that 1 meters. Now, when we look at a prefix multiplier that multiplies and makes it bigger, for example, kilo. So let's look at kilometer. This means that this multiplies by 1,000, essentially. So 10 times 10 times 10, that's 1,000. And what you end up getting for 1 kilometer is 1,000 meters. So each of these is associated with a certain number. Each prefix has a certain number or factor to it. They also have a symbol, so we can put this symbol in front of just the symbol for the unit, and then we end up getting that basically like an abbreviation. So your job is to practice using these. You don't necessarily have to memorize them off the top of your head each time, but know how to use them. And we're going to get to that part when we start using dimensional analysis, and we're going to practice converting between multipliers. So I'm not sure if you guys noticed, but on that chart where we talk about the International System of Units, the SI units, volume for some reason isn't on there, and that's because volume is actually a derived unit. It's not a one-dimensional unit. It comes from the length, the width, and the height of something. So the volume is how much space something takes up, and like I said, that is calculated through different dimensions, not just one dimension. And here you have some pretty common terms. So cubic meter, it's a cube with an edge length of 1 meter. A liter is actually a cube with an edge length of 1 decimeter, which I know is kind of weird, but you'll use liter and don't worry about it too much. A cubic centimeter you'll see more often, especially when we do that density lab, and for the problems that we're going to be doing later on in this chapter. A cubic centimeter is also equal to 1 milliliter. Please keep that in mind. Now, something else that is a derived unit is density. So density is how much mass you have per a certain amount of space. So the space is that volume, so it's mass divided by volume. The most common unit that you'll see for this in this class is grams per centimeters cubed or grams per ml. Remember, 1 centimeter cubed also equals 1 ml, so that's typically what you'll see. Later on, when we get to gases, you'll see gas per liter sometimes. So in this example, we're going to be calculating density. So again, remember, we're going to use our method. So first we're going to state the problem, and to state the problem we need to read the problem. So that's always your first thing to do. So what is the density of a cube of iron with a mass of 3.9 grams and a volume of 0.49 centimeters cubed? So we know that we have to solve for the density, basically, right, of a cube. Now, for number 2, we're going to clarify the known versus unknown. So our known, K, and our unknown, UK. So known, we have 3.9 grams for our mass, and then for our volume, we have 0.49 centimeters cubed. We also know that density equals mass over volume. We know we have both the density and the volume. What we need to solve for is density. So our unknown is our density. This is a pretty straightforward problem. So now we can solve, right? We know what we have. We have the mass and the volume. We just need to plug and chug. So D equals our mass. And then once you calculate that out, you should end up getting So this is a pretty straightforward problem, very simple, and this is to get you acclimated to using this method of establishing our unknowns and our knowns. And now we are going to move on to a more complicated problem. So in this example, we are calculating density again, finding volume of a cube. So in this case, the problem doesn't explicitly give us the volume. We actually have to go and calculate it ourselves. So it's asking for density, right? So let's find our known and our unknown. So for known, we have our mass, and then we have a length of 0.757. And specifically, I want you to notice that it's a cube. So I'm just going to give a short reminder about how to find the volume of either a prism, a rectangular prism, or a cube. It's going to be length times width times height. In this case, since we have a cube, we can just actually, like the name says, we can cube this value. So multiply it by itself 3 times. And then you end up getting, so our unknown right now is our volume and our density, right? So what you end up getting when you cube that in the calculator is around 0.4337. And the unit also cubes, so not just the actual number. So now we have our volume, we have our mass, so now we can calculate the density. So again, plug and chug. And then you end up getting 10.51 grams per centimeter cubed. So we've been talking about measurements so far, but we haven't talked about the actual value and how the instruments that we use and the person that measures affects the measurement itself. So every measurement that you ever take in a lab using an instrument will have a certain level of uncertainty. So uncertainty is how close the value that you get, the measurement, is to the actual true value. And this uncertainty depends on the device, so the instrument that you're using, or if it's something that is visual, then that will depend on the user as well. So let's say you're reading a temperature. I'll look at the thermometer and I'll just be like 25, it's around 25. I would round it out probably. But a newer student will probably look at it and, analyze it more because, you don't want to get it wrong. So the student will probably take longer and end up choosing 25.1 as their measurement. So that's what we mean by user. Now, the amount of digits that you take in your measurement are called the significant figures of your measurement. The last uncertain digit, and that's what we mean whenever I was talking about the me versus a student measuring a temperature. So I would look at it and say it's 25.0 versus a student could look at it and say it's 25.1. That last measurement, so 25.0 compared to 25.1, that last number is your uncertain digit because that's the one that you're estimating. So there are very specific rules for identifying and using significant figures. So a big idea that I want you to understand is that the more sig figs that you have, the greater the certainty of the measurement. So that means that your instrument is very delicate. It can measure a lot of sig figs, so a lot of decimal points, and that means it's closer to the true value. But the rules that we use to identify sig figs begin with these. So all non-zero digits are significant. So you see these pink ones here, 2, 8, 3, these for sure are significant. Any non-zero, so this 5 and this 4 and this value are significant. Interior zeros, so interior zeros are between two non-zeros. So here you have a 4 and an 8, and between it you have a 0. So it's a 408, right? That 0 is significant. Here you have 7.030, and there's actually another number right after that O, that last O, but you can't see it because the camera's in the way. But these zeros, because they're in between, they're sandwiched. You can think of these as sandwich zeros. They're significant because they're between non-zero digits. So the first two rules are very straightforward. These next few rules are a little bit more they have more specifics to them, more details. So leading zeros are zeros that you will see at the front of a value, and these are not significant. The reason for this is because all they are is to locate the decimal point, and you can actually convert these to scientific notation with no problem, and it won't really affect the value at all. The next one is trailing zeros. Trailing zeros, think of trailing like at the end behind you. So these, again, a little bit more complicated. So whenever you have trailing zeros after a decimal point, so for example, these right here, these, since they're after a decimal point, they're significant. Trailing zeros before a decimal point, for example, that one, but after a non-zero number, are always significant. So these are another example of that right there. This is, I would say, the most tricky one. So trailing zeros before an implied decimal are ambiguous and should be avoided. I don't want to say tricky, I want to say that this is like the weird specific case that you want to be able to recognize and know that it's ambiguous and that you shouldn't use something like that. So in this case, because there's no decimal point at all, you don't know if those zeros are actually significant or not. So you want to avoid this type of case. In all these other cases, because we have that decimal point right there, then you know that they're all, anything after it is significant, so it's pretty straightforward. In this case, you have 2, 3, and 4. And then decimal points placed after one or more trailing zeros are significant. So as long as you have that decimal there, then you know that those zeros are significant. So here you have 4 sig figs. So the next type of number that we are learning about in relation to sig figs are called exact numbers. So exact numbers have an unlimited number of sig figs. So anytime you have an exact number and you're using it to calculate something, you will not take it into account. So basically you ignore it and you only look at what you're given and any other types of conversion factors that don't fall into these categories. So The first type of exact number is pretty easy to conceptualize. It's numbers that we can essentially count. So let's say you're counting the people in a room. You can't count like a half a person. It's either, let's say you have 28 people. You don't have 28 and a half. You don't have 27 and a half. It's 28. So that's an example of an exact number, something that we can count. Next, we have numbers that we have defined. These are certain conversion factors. The first of that type is when you're going from one American unit, so let's say inches, to another American unit. That's an exact number. This unit equation, which we're going to talk about, 12 inches equals 1 foot. This has an unlimited number of sig figs because it's an exact conversion factor. The next type is when you're going from American to metric. And then the final type is when you're going from one metric unit to another metric unit, and the only difference is the prefixes that you have. So for example, here you have a gram to a kilogram. All of these three types of conversion factors have a limited number of sig figs. They are all exact numbers. So whenever scientists take measurements of data or something that they're observing, it doesn't usually just get recorded and that's it, they're done. Usually these measurements will be taken and you'll have to calculate something in order to get like a final result that you can present. So whenever you do these manipulations or calculations to your data, you have to keep your significant figures into account. And this is to prevent losing any precision of anything that you measured. So we don't want to lose or gain any precision, because then that would reflect on something that is not true, essentially. If your instrument can measure only to a certain degree of like sensitivity, then you can't just add significant figures to make it look like it has more precision than it does. And to help you understand why it's so important to keep significant figures in calculations, I'm going to give you this example. So you are going to the bank to take out some money. Specifically, it's $1,100. So you tell the teller, and the teller is kind of being lazy. They don't want to take it into account. Let's say that banks, they actually took sig figs into account. And this teller doesn't want to do it before they take out the money from your account and give you your money in $100 bills. So what the teller does is they just round it. They're like, that's close to 1,000. So the teller ends up giving you just 10 $100 bills. Something is not adding up, right? Something got lost along the way. So this is a good example of how you can lose precision. So in this case, you are losing $100, and that's not an ideal situation. So it's the same idea that we want to keep sig figs in data and in calculations. So there's two major rules when considering sig figs in calculations. The first rule has to do with multiplication and division. So I'm going to start by just showing you these examples. So let's say you have this value which has 4 sig figs, and this value has 5, and then this final value has 2. Remember this is a leading zero, which is never significant, so that's why there's only 2 right there. But whenever you multiply these out, what you're going to end up doing is you're going to get a larger number, but at the very end you only want 2 sig figs, and that has to do with the fact that your limiting value of sig figs is 2. So the number that you use in this calculation that had the least amount of sig figs is the one that determines how many sig figs you have at the end. So you will round the answer to the same number of digits as the number with the least amount of sig figs. So basically you look at your numbers and you're like, okay, this one has 4, this one has 5, this one has 2. My final answer is going to have 2. Now this division is just another example. So this one has 5 sig figs, this one has 3. Your final answer is going to have 3 sig figs. So the next rule is about adding and subtracting. And let's say you have these 3 values right here. We're going to look at the numbers after the decimal point. So the number with the least number of digits after that decimal point, and in this case it's this one right here, will be the one that determines how many decimal places you have at the end. So I know this is kind of strange because this rule kind of doesn't really have anything to do with sig figs per se, but it ends up determining how many sig figs you have at the end. So here you see that this one has 3 numbers after the decimal point, 2 numbers after the decimal point, and then 4 numbers after the decimal point. You add it all up, you take all the values, all the digits you possibly can, and then at the end for your final answer you look at the one that had the least, which was 2, so you're only going to have 2 decimal places here. And then the same with subtraction. This one only had 1, so you're only going to have one digit after the decimal point for your final answer. So if you're doing a problem that requires like multiplication and then division and then some sort of subtraction, anything like that, that's a multi-step problem, you will take the sig figs and decimal places into account at the very end. So you keep as many digits as possible until the very last operation, and whatever final answer that you get, that's the one that's going to determine how many sig figs or decimal places you need to have in your final answer. Now, when that happens, you're basically going to have extra digits, right? So you're going to have to round. If the last digit is less than 5, you round down. If it's greater than 5, you round up. Or if it's 5 or greater, you round up. So let's take a look at some examples. So here we have 5.37. We only want 2 sig figs, let's say. So you look at that last number after the one that you want. You know you only want 2. So you look at the one right next to it. This is greater than 5, so it rounds up to 5.4. Now in this last example, you only look at the digit to the right of the last one that you want. So we know we only want 2 sig figs. We're going to have to keep this number. What we're rounding is somewhere over here. You're not going to look at the 9. You're going to look at that 4. So you ignore that 9. You look at whatever's next to the last one that you need. So that's why this rounds to 5.3, and you don't look at that 9, you ignore that 9. So now we're going to apply everything that we've learned and first identify sig figs. So here we are identifying, and then on this next example we will be calculating an answer with the correct number of sig figs. So on this first problem, we see that we have some non-zero digits surrounding an internal 0 in between them. So that must mean that all of these digits are significant because that 0 is sandwiched in between. So here we have 4 sig figs. Here we have a pretty big number. We have 9,100, but we don't have any decimal points right here at the end. So this is a case where it's ambiguous and we can't tell whether these 2 zeros are actually significant or not. So your answer for this would be ambiguous. Now here we have a bunch of leading zeros, and we know that leading zeros are never significant because you can just convert them to scientific notation and it takes them all away. So you end up having just 2 sig figs here. Now on this next example, we have some addition. It's all addition actually. So you'll be practicing the multiplication and division on your own, and then we will practice it together during our problem solving session. But here we have a pretty simple one. So we just have 2 different numbers and we're adding them. In this case, what we're going to look at is the number of decimal places. So for addition and subtraction, it's decimal places. So here we have 3 decimal places. Here we have 1 decimal place. So we're going to add it all up, but at the very end, we need to take into account those decimal places. So once you add this, you end up getting this number. 1, 3. Sorry, that's kind of ugly. But what we need to do is find out how many decimal places we actually need. And it turns out we only need 1, since this one only has 1. It limits our final answer essentially. So we're only going to need this one right here. And because this one right there is less than 5, then we don't round up for that last value. So we end up getting 128.0, and that's our final answer. Now in this case, we have first one operation being done, and then one after. So whenever you have something in parentheses, remember PEMDAS, anything in parentheses will come first. So we're going to do this operation first. Now when you add these two up, you end up getting 35.14. But we know that because this is addition and it's limited by decimal places, we have to take that into account. So here, both of these have 2 decimal places, so we can actually just keep both of those, and we know that our final answer will be affected by the fact that this answer right here has 2 decimal places. So let's label that 2 decimal places. Now we're adding to that 101. 101 has 0 decimal places. So that is going to affect our final answer. Now when you add this all up, you end up getting 136.14, but we know that's not our final answer. And because this right here doesn't have any decimal places, we know that we are going to have to round. So instead of 136.4, we don't want any decimal places, and because this 1 is less than 5, then we are going to leave it at 136. And that's our final answer.